Imagine something the size of a mountain hurtling toward the sun at over 60 kilometers per second. A cosmic drive-by from the edge of interstellar space. That's 3IATLAS, a wanderer that didn't even grow up in our solar system. It's an interstellar object, one of the few ever caught sneaking through our cosmic neighborhood. Discovered in 2019, it's been drifting for millions, maybe billions of years. A lonely rock with a passport stamped by multiple star systems. But what if its journey ended with a spectacular finale? A head-on collision with the sun? Good evening, curious minds. Science doesn't need to shout to be fascinating. Sometimes it's best enjoyed the way you'd enjoy a late-night conversation. Quietly, with a cup of tea and maybe the soft hum of a fan in the background. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing. No pressure, only if you enjoy these calm journeys through the universe. Now, let's begin. Before we imagine that fiery ending, let's rewind to the beginning, or at least as close to a beginning as we can guess. 3IATLAS wasn't born anywhere near here. It likely formed in the chaotic nursery of another star system, a place where young suns were still learning how to shine and planets were jostling for stable orbits. Somewhere in that early chaos, a gravitational scuffle, maybe between giant planets, gave this rock an astronomical eviction notice. One wrong move, one planetary shove, and it was tossed out like cosmic trash, flung into the darkness between stars. But space doesn't do trash. It does eternal drifting. For eons, 3IATLAS traveled alone. No sunlight, no warmth, just endless night, colder than physics really should allow. It's the ultimate introvert of the cosmos, wandering where even light rarely goes. Occasionally, it would pass near another star, maybe briefly illuminated, maybe even tugged a little off course. But, for the most part, it just kept going. Imagine an ancient traveler walking through the galaxy with no destination, just momentum and memories of where it came from. When it finally crossed paths with our solar system, we barely noticed at first. It was faint, dim, and fleeting, like spotting a firefly at the edge of a floodlight. Discovered by the Atlas survey in Hawaii, this object instantly caught astronomers' attention because its trajectory didn't match anything that belonged here. Everything in our solar system, from Mercury to Pluto, orbits in predictable ellipses around the sun. 3IATLAS, though, was cutting across those orbits on a hyperbolic path, a clear sign that it came from far beyond. That's what made it only the third interstellar object ever discovered, after Oumuamua in 2017 and Borisov in 2019. You could say 3IATLAS is part of a very exclusive club of galactic tourists, and it didn't even bother to RSVP. Unlike Borisov, which looked like a classic comet, 3IATLAS was already falling apart when we found it. By the time telescopes locked onto it, its icy surface was fragmenting, crumbling under the sun's heat like an ancient snowball melting in slow motion. It was a short visit, but an intriguing one. Scientists love objects like this because they're physical evidence that planets form everywhere, not just here. Every interstellar visitor carries with it the fingerprints of its home system, its chemistry, its structure, maybe even hints of what kind of star once warmed it. Studying 3IATLAS, even from afar, gave astronomers a taste of alien geology, a sample of someplace we'll never visit. It's like finding a seashell in the middle of the desert. It doesn't belong, but its existence tells a story about oceans far away. Now, imagine for a moment that 3IATLAS didn't just swing by and disappear into the void again. Imagine that its orbit took a more tragic turn, a direct plunge into the sun itself. Suddenly, this quiet interstellar traveler becomes the main character in one of the most extreme endings imaginable. After billions of years wandering between the stars, it would finally meet its end in a roaring sea of plasma. There's something poetic about that. A journey through the coldest emptiness ending in the hottest fire in the solar system. But before we light the fuse, it's worth appreciating how much of an underdog story this is. 3IATLAS is small by cosmic standards, maybe a few hundred meters across. The sun, meanwhile, is so massive that you could fit over 1 million Earths inside it. So this is not exactly an even match. It's like throwing a snowflake into a furnace and expecting an explosion. And yet, even that tiny moment, an interstellar object meeting a star, would be rich with scientific drama. Because to astronomers, the story isn't about who wins. It's about what happens in those few fleeting seconds before everything turns to vapor. As it approached the sun, 3IATLAS would be racing through a gravitational field that makes roller coasters look like tricycles. It would accelerate relentlessly, heating up, glowing brighter, its surface boiling away layer by layer. If there were a soundtrack, this would be the crescendo. Ancient dust meeting the ultimate inferno. The collision wouldn't be quiet or subtle. It would be an interstellar encore performed in ultraviolet and X-rays, visible across millions of kilometers. And that's the beauty of cosmic imagination. When you picture 3IATLAS plunging into the sun, you're not just thinking about rocks and plasma. You're thinking about time itself. This object could have started its journey before humans even existed, before Earth's continents settled into their current shapes. It may have drifted past dying stars, through supernova shockwaves, and across entire arms of the galaxy, only to end up here, colliding with our local star in a blaze of physics and poetry. The universe has a strange sense of timing. Sometimes it lets travelers wander forever. Sometimes it arranges their finales with dramatic precision. And if 3IATLAS ever did crash into the sun, it wouldn't just be a collision. It would be a cosmic punctuation mark at the end of a story billions of years in the making. The quiet traveler from the deep dark finally finds its light by becoming part of it. 3IATLAS isn't your average asteroid. It's a cosmic drifter without a home orbit. Think of it as that mysterious traveler who shows up in town, buys a coffee, and disappears before anyone learns their name. It doesn't circle our sun. It doesn't belong to any planetary family. And it certainly doesn't care about fitting in. It's a free agent in the vast cosmic game, obeying only the cold, mathematical laws of gravity. Most rocks in our solar system follow predictable routes. Tiny players in a gravitational symphony directed by the sun. They circle obediently in belts, loops, and ellipses, pulled gently but firmly by solar gravity. 3IATLAS, on the other hand, takes the freedom of movement clause to interstellar extremes. Its path isn't a circle at all, it's a hyperbola. That means instead of looping around and coming back, it swoops in close, nods politely to the sun, and speeds off forever. It's a one-time visit, a cosmic drive-through. To understand what makes 3IATLAS so fascinating, you have to imagine its origin story. Not here, but light years away. Somewhere in another solar system, billions of years ago. Young planets and asteroids were forming out of swirling disks of gas and dust. The process wasn't peaceful. Massive planets, probably the size of Jupiter or larger, played an early game of interplanetary bumper cars. Some smaller rocks got lucky, settling into stable orbits. Others got unlucky and were flung out of their systems entirely. Those exiles became the galaxy's vagabonds, pieces of planetary leftovers wandering between the stars. 3IATLAS is one of those wanderers, a refugee from a solar system that's long since calmed down, or maybe even died. It may have witnessed its original star flare up and fade away before drifting off into the quiet dark. For all we know, its home system could now be just a white dwarf, surrounded by the ghosts of planets it once held close. 3I. Atlas carries no record of its birthplace except its chemistry, frozen deep inside its crust. It's like a fossil without a label, telling a story written in elements instead of ink. Now, when astronomers first spotted 3IATLAS, they noticed something intriguing. It wasn't behaving like a typical asteroid or a comet from our own solar system. It was already disintegrating. Its surface was unstable, shedding fragments as sunlight hit it. That hinted at a fragile, volatile composition. Probably a mix of rock and frozen gases like carbon dioxide, methane, and ammonia. In other words, this was not some iron chunk of space metal. It was more like a half-melted snowball that had spent eons in a freezer the size of the galaxy. What's fascinating is that this kind of mixture tells us a lot about where it came from. In our solar system, comets formed farther from the sun, in colder regions like the Kuiper Belt or the Oort cloud, where ice could survive. If 3IATLAS formed under similar conditions, its original star system must have had a frost line, a region far enough from its star for ice to exist. That means it came from a place with familiar physics, perhaps even a family of planets not too different from ours. It's comforting, in a cosmic way, to realize that other solar systems may follow the same recipe book as ours: dust, gas, chaos, and time. But its journey through interstellar space would have changed it in ways we can barely imagine. Out there, between the stars, radiation from distant suns and cosmic rays constantly bombard anything exposed. Molecules on its surface would have been rearranged, broken apart, and fused back together into complex, carbon-rich compounds. It's like space's version of slow cooking, billions of years of gentle cosmic roasting. By the time it entered our solar system, 3IATLAS was ancient, altered, and scarred by the deep freeze of time. What does an object like that look like? Not shiny, that's for sure. Probably dark, almost pitch black. Most interstellar objects have surfaces coated in organic molecules called tholins, which are basically cosmic soot. They form when ultraviolet light breaks apart simple gases, like methane and nitrogen, then reassembles the fragments into gunky carbon chains. The result is a reddish, tar-like material that absorbs most light and reflects very little. So, 3IATLAS likely looked like a lump of charcoal that's been dunked in frozen ammonia. Not the prettiest traveler, but certainly the most mysterious dinner guest at the solar party. What truly sets it apart, though, is its trajectory. It's not just moving fast. It's moving at speeds our local asteroids can only dream of. Over 60 kilometers per second relative to the Sun. To put that in perspective, that's fast enough to cross the entire Earth in under 7 minutes. And yet, in cosmic terms, that's considered leisurely. The vastness of space makes even outrageous speeds feel like slow motion. The reason for that hypervelocity is the gravitational slingshot it got when it was ejected from its home star system. When a giant planet flings a smaller body outward, it's essentially transferring some of its orbital energy to it, like a slingshot pulling back and releasing a pebble. Once that pebble escapes the gravitational well of its home star, it's free forever, bound to nothing. 3IATLAS is living proof that once you leave a solar system, you don't just stop. You drift endlessly, unless something as massive as another star happens to pull you in. And that's the part that makes interstellar objects so rare and fascinating. The galaxy may be filled with them, but they're hard to spot because they're small, dark, and fast. 3IATLAS was only visible for a short time before it fragmented into pieces too small to track. If telescopes hadn't been watching at the right moment, we'd never have known it existed. That's a humbling thought. Thousands of other interstellar travelers could be passing through right now, unseen, gliding silently through the outer edges of our solar system, like ghosts from other worlds. Every time one of these drifters enters our view, it reminds us that our solar system isn't isolated. It's part of a much larger dynamic galaxy where materials and stories are constantly exchanged. 3IATLAS isn't just a rock. It's a messenger from somewhere else. It tells us that planets form, break apart, and scatter their pieces across the cosmos. It's evidence that creation and destruction are universal habits, not local quirks. So when you think of 3IATLAS, don't imagine just a chunk of ice and dust. Imagine a relic older than humanity, shaped by forces we'll never witness, carrying secrets of stars we've never seen. It's not a resident of our solar system. It's a visitor, a wanderer, a cosmic hitchhiker that reminds us that even in the vast emptiness of space, everything is still connected. It may have no address, but it belongs everywhere. Getting something to actually hit the sun isn't easy. It's like trying to hit the bullseye on a dartboard while standing on another moving dartboard. The sun's immense gravity makes trajectories curve, but most objects end up slingshotting around it instead of plunging in. For 3IATLAS to collide head-on, it would need a nearly perfect trajectory, an astronomical hole-in-one. But let's say, just for fun, that physics decides to give us a show. To understand how hard that is, imagine space as a giant, invisible trampoline. The sun sits in the middle, pressing down so deep that anything nearby rolls toward it. But things in space rarely fall straight in. They orbit. Every planet, asteroid, and comet is basically falling toward the sun. But they keep missing because they're also moving sideways at just the right speed. To actually crash into the sun, something has to lose almost all its sideways motion. In other words, it has to stop orbiting and start diving. 3IATLAS, being an interstellar visitor, is already traveling fast. Too fast, in fact. Its hyperbolic trajectory means it's not captured by the sun's gravity the way local comets are. Instead, it's just passing through, using gravity like a cosmic on-ramp to swing around and shoot off again into the dark. For it to hit the sun, it would need to approach at exactly the right angle and speed, like a billiard ball shot straight at the pocket from across the table, without even touching the sides. That's a near impossible aim. Even spacecraft built by humans and guided by precise navigation rarely get close to the sun's surface. Take NASA's Parker Solar Probe. It's the fastest human-made object ever, traveling hundreds of thousands of kilometers per hour. And even it only dips into the sun's outer atmosphere, not the blazing surface itself. That's how difficult it is to aim at a star. Gravity wants to pull you in, but momentum keeps you orbiting around. Still, let's imagine that the cosmic geometry lines up perfectly for 3IATLAS. It approaches from deep space on a trajectory that threads the narrowest needle in celestial mechanics. The sun's gravity begins to tug at it from millions of kilometers away, accelerating it faster and faster. By the time it's halfway between Mercury's orbit and the sun, it's moving at nearly 600 kilometers per second. At that speed, it could circle Earth 15 times in a single minute. Space doesn't do slow motion. It does terrifyingly fast obliteration. But there's another factor at play: radiation pressure. The sun isn't just pulling objects inward with gravity. It's also pushing them outward with light. Yes, light has no mass, but it carries momentum. Photons, tiny packets of energy, smack into the surface of anything in their way. For small particles or lightweight debris, that push can be significant. It's why comets develop tails that stream away from the sun. As 3IATLAS gets closer, sunlight would start blasting its surface with radiation pressure strong enough to peel off layers of ice and dust. It's like approaching a bonfire, so intense it starts melting you before you even reach it. This process is called sublimation, the transformation of solid ice directly into gas. For a fragile object like 3IATLAS, sublimation would be catastrophic. Jets of vapor would erupt from its surface, acting like thrusters that nudge its course unpredictably. That's one reason comets often break apart before they even reach the sun. The physics of melting ice in space is chaotic. It's like trying to steer a car that's simultaneously on fire and turning into steam. If 3IATLAS were a more solid, rocky body, it might survive the journey longer. But even then, the forces acting on it would be brutal. The sun's tidal gravity, the difference in pull between the near side and far side of the object, would stretch it, strain it, and eventually tear it apart. It's the same reason comets often disintegrate into chains of fragments when they get too close to their star. The technical name for this line of destruction is the Roche limit, but you can think of it as the distance where gravity stops playing nice and starts playing tug-of-war with your atoms. As 3IATLAS spiraled in, every kilometer would crank up the temperature. The outer solar atmosphere, the corona, can reach millions of degrees Celsius, though it's so thin that the object wouldn't instantly vaporize. Instead, it would experience what scientists call thermal ablation, where its surface steadily burns away layer by layer. The closer it gets, the faster it goes, and the hotter it becomes. It's a self-destructive feedback loop. Speed fuels friction, friction fuels heat, heat fuels destruction. By the time it was just a few 100,000 kilometers from the sun, the object would be glowing fiercely, radiating energy in visible and ultraviolet light. Any telescope aimed its way would catch a brief but beautiful spectacle. A bright, streaking flame cutting across the solar glare. The final moments before impact would be spectacular. A swirl of vaporized rock, glowing plasma, and magnetic chaos as the debris collides with the sun's outer layers. Ironically, even at this stage, there's a decent chance 3IATLAS wouldn't make it to the actual surface. It would likely disintegrate completely in the corona or chromosphere, long before reaching the sun's visible photosphere. That's like a meteor burning up in Earth's atmosphere before ever touching the ground. The sun's atmosphere may be thin, but at those speeds and temperatures, it's enough to turn even a mountain-sized rock into vapor. If, by some miracle of density, a few fragments did survive the journey and plunge into the photosphere, their end would be instantaneous. The surface of the sun isn't solid. It's a roiling sea of plasma, a million-degree soup of ionized hydrogen and helium. The moment 3IATLAS touched it, it would be absorbed and vaporized, its material dispersed throughout the solar plasma like sugar dissolving in boiling water. So, yes, crashing into a star is far from easy. It requires perfect aim, cosmic luck, and the kind of suicidal trajectory that even physics might call ambitious. Most things that get close to the sun either slingshot away or burn up before arrival. Hitting the sun dead on is a rare, dramatic exception to the rule, a final act in which every law of motion, energy, and heat comes together in one bright, fiery instant. It's humbling to think that the odds are so stacked against such a collision. Space isn't just empty, it's precise, governed by invisible equations that decide whether a rock becomes a planet, a comet, or just a brief flash of light. For 3IATLAS, to end its billion-year journey by actually striking the sun would be one of the most cinematic finales in the universe. A traveler from the stars, guided by nothing but gravity and chance, finally dives straight into the cosmic furnace. Proof that even in a universe ruled by physics, there's still room for a spectacular accident. When 3IATLAS finally meets the sun, it won't exactly splash. It'll vaporize long before it even touches the surface. The sun's outer atmosphere, the corona, is millions of degrees hot. The rock would begin to disintegrate hundreds of thousands of kilometers away, glowing brighter than fireworks at a galactic festival. The entire collision would be over in seconds, but the energy released would be immense, turning the visitor into a brief, brilliant flare before it's swallowed by the solar inferno. The moment of impact, if we can even call it that, begins long before any physical contact. Space doesn't deal in splat. There's no solid ground waiting for 3IATLAS at the end of its journey, only layers of increasingly violent plasma. The sun's outermost region, the corona, stretches millions of kilometers into space and is paradoxically hotter than the surface beneath it. That's like standing near a bonfire and discovering the smoke is hotter than the flames. Scientists are still trying to understand why. Some blame tangled magnetic fields snapping like cosmic rubber bands. Others suspect waves of charged particles whipping through the gas. But whatever the reason, the corona is no gentle welcome mat. As 3IATLAS hurtles into that searing halo, the first thing that happens is the vaporization of its outer layers. Any ice or volatile materials, frozen carbon dioxide, methane, ammonia, would flash instantly into gas. The rock's crust would begin to glow, then liquefy, then atomize as molecules are ripped apart by heat and radiation. The object wouldn't so much crash as dissolve, each atom surrendering to the sun's energy field in a cascade of light. It's cosmic cremation on a spectacular scale. The brightness of that event would depend on size and composition. If 3IATLAS were a few hundred meters across, the total energy of its demise could rival a small solar flare. For a few brief moments, it might even outshine parts of the sun's surface, a glittering point of destruction, visible through specialized telescopes. To us, watching from Earth, it would look like the tiniest flicker on the solar limb. Here, then gone. But to the instruments tracking it, it would be a treasure trove of data, a flash rich with elemental fingerprints, revealing what the interstellar traveler was made of. Every second of that disintegration would be a physics experiment in overdrive. The outer layers would be stripped by radiation pressure, leaving a core that's heated unevenly. That imbalance could cause it to fracture explosively, sending fragments in all directions. Each shard would follow its own fiery fate, burning up at slightly different altitudes. From a distance, it might resemble a cosmic sparkler, thousands of glowing fragments cascading into plasma. In those final moments, 3IATLAS would become not one object, but a cloud of incandescent debris, each piece contributing its own brief signature to the sun's light. Now, let's talk about heat in terms we can feel, if we dared. The corona's temperature can reach over 1 million degrees Celsius. That's so hot that the very idea of solid stops making sense. At that temperature, atoms lose their electrons entirely, forming plasma, a sea of charged particles that behave like a gas, but with a personality disorder. For 3IATLAS, entering that environment would be like diving into a storm of electrified fire. The heat transfer wouldn't be gradual. It would be instant, absolute, and terminal. And then there's the light. As the rock's material vaporizes, the atoms and ions emit radiation at specific wavelengths. Iron might glow in bright green and yellow lines, carbon in ultraviolet, oxygen in soft X-rays. Each element sings its own spectral note, creating a luminous symphony that astronomers can record and analyze. In that moment, the sun becomes both destroyer and teacher, obliterating the visitor but revealing its secrets in the process. Every flash of light is a clue, a message from another solar system, written in plasma and photon. If we could somehow slow time to watch this unfold in detail, it would be mesmerizing. Imagine the dark silhouette of 3IATLAS shrinking against the blazing corona. A thin, shimmering halo forms around it as gases erupt from its surface. Then, an eruption of light, a blossom of vapor, and charged particles expanding outward like a blooming flower of fire. The entire event might last no more than 20 seconds. But those seconds would contain enough drama to keep scientists busy for decades. The aftermath would be fleeting but fascinating. The vaporized material, iron, carbon, oxygen, silicates, would disperse into the solar plasma, temporarily enriching that region with alien matter. Solar winds would sweep those particles outward, blending them into the stream of charged particles constantly flowing from the sun. Some of those atoms, now fully ionized, might even travel all the way to Earth, carried by the solar wind. The next time you feel the warmth of sunlight on your skin, a few of those particles could, in theory, be remnants of something that once came from another star. That's not just poetic. It's technically possible. For the sun, though, the whole affair is barely a hiccup. The energy released by the total annihilation of 3IATLAS would be minuscule compared to the Sun's daily output. The Sun converts 4 million tons of its own mass into energy every second. Compared to that, even a mountain-sized object adds less than a raindrop to a hurricane. The difference is dramatic. We would see a spectacular burst of radiation, but the Sun wouldn't even flinch. It's the cosmic equivalent of swallowing a fruit fly mid-yawn. Still, the symbolism of the moment is hard to ignore. A rock born in another star system, wandering for eons, finally finds its end by diving into a new one. It's both an ending and a reunion. The atoms of 3IATLAS, forged long ago in the heart of another sun, would return to stellar fire. The cycle completes itself. Matter, after all, doesn't vanish. It just changes costume. If we were to give this event a human metaphor, it would be like a traveler returning home after an impossible journey, only to be welcomed by the warmest, most fatal embrace imaginable. There's beauty in that tragedy. The Sun doesn't destroy for cruelty's sake. It simply reclaims what the universe lends it. In the grand ledger of cosmic energy, nothing is lost. It's all just recycled, brighter than before. And so, the moment of impact isn't really a crash, it's a transformation. A billion-year story condensed into a few seconds of light. 3IATLAS would vanish completely, but in doing so, it would leave behind something far greater. A reminder that even across interstellar distances, every atom in the universe is still part of the same ongoing conversation. The Sun may be the final chapter in 3IATLAS's story, but it's also the beginning of a new one, written in the language of light, heat, and eternity. To telescopes on Earth, that impact would be like watching a snowball evaporate in a flamethrower, but in slow motion. Instruments could detect ultraviolet and X-ray bursts as the interstellar material interacts with the Sun's atmosphere. It'd be a rare treat, a cosmic autopsy revealing the chemical makeup of something from beyond our solar system. Astronomers would cheer. The Sun, on the other hand, wouldn't even burp. For scientists who dedicate their lives to studying light from things impossibly far away, a moment like this would be the equivalent of winning every astronomy lottery at once. Imagine it, a confirmed interstellar object carrying alien dust and minerals, smashing headfirst into the Sun in full view of a planet packed with telescopes. That's not just rare, it's once in a civilization rare. In the same way paleontologists dream of finding a perfectly preserved dinosaur, astronomers dream of witnessing an event that both destroys and reveals something never before seen. The first wave of excitement wouldn't come from the visual spectacle. It would come from the data. Around the world, space observatories would tune their instruments like musicians preparing for a symphony. NASA's Solar Dynamics Observatory would point its sensitive cameras toward the Sun's limb. The European Space Agency's solar orbiter might already be in position to capture the event from another angle. The Parker Solar Probe, slicing through the Sun's outer atmosphere on its daredevil orbits, could record the electromagnetic shockwave firsthand. Every one of these machines would be watching, waiting for the moment that a faint, fast-moving speck transforms into a brilliant flare of alien chemistry. The data would pour in across the spectrum. Optical telescopes would see the flash in visible light, a short-lived spark barely distinguishable from the Sun's chaotic surface. But ultraviolet and X-ray telescopes, they'd be the real witnesses. As the interstellar material vaporizes, its atoms would emit light at very specific wavelengths. Those spectral lines act like fingerprints. Hydrogen glows differently from carbon, iron differently from oxygen. By breaking down the light from the impact, scientists could decode exactly what 3IATLAS was made of. It's forensic science at a cosmic scale. The idea of reading chemistry through light may sound abstract, but it's one of the oldest tricks in astronomy's book. It's how we know what stars are made of without ever visiting them. When the light from a star, or in this case, a violent vaporization, passes through a prism or diffraction grating, it splits into a rainbow of colors. Within that rainbow are dark or bright lines, each corresponding to an element. Astronomers call this spectroscopy, but it's really more like reading the universe's barcodes. So when 3IATLAS burns up, it's not just a show of colors. It's a message. A message that says, here's what other solar systems are cooking with. And that's where the excitement truly lies. Every interstellar object is a sample of another world's building materials. By studying its composition, we can learn what kinds of stars, planets, and processes exist beyond our cosmic neighborhood. Maybe 3IATLAS formed in a system richer in carbon than ours. Maybe its ice held exotic compounds that never form in our solar system's colder regions. Each element or molecule would tell a story about the chemistry of another sun. A sun that might be long dead, but whose remnants now write their signature in light across our skies. While telescopes feast on the data, solar physicists would have a field day studying how the impact itself affects the sun's atmosphere. When a high-speed object slams into plasma, it doesn't just vanish, it transfers energy. Shock waves ripple through the sun's outer layers, triggering bursts of X-rays and possibly even radio emissions. These ripples could reveal how energy moves through the corona, one of the great mysteries in solar science. It's like dropping a stone into a pond made of fire and watching how the ripples dance. And then there's the visual spectacle itself. To the naked eye, even through filtered solar lenses, you wouldn't see much. Just the same blinding sphere of light. But specialized solar telescopes could catch something extraordinary. They'd see a brief, pinpoint flare, an eruption of brilliance, perhaps with tendrils of gas swirling outward as the vaporized material merges with the sun's plasma. The colors would shift rapidly as different elements burn away. In a matter of seconds, the entire event would fade back into the blinding uniformity of the sun's glare, leaving no trace except in the data logs of observatories across the world. For astronomers, those few seconds of data would become years of work. Teams from every continent would analyze the light curves, the energy output, the spectral signatures. Papers would flood scientific journals with titles like Spectroscopic Analysis of the 3IATLAS Impact Event. Some researchers would model the vaporization physics. Others would trace the origin of its isotopic ratios to figure out which kind of star system it came from. It would become one of those scientific moments that define a generation, not because of its danger or its grandeur, but because of its sheer informational richness. And of course, there would be the public reaction. Social media would explode with images from NASA and the European Space Agency. Headlines would read, "Alien object collides with the sun." Documentaries would be greenlit within hours. Someone on the internet would inevitably suggest it's an alien probe, because the internet will always internet. And while the memes roll in, astronomers would quietly sip their coffee, grinning. Not because they disproved alien theories, but because they just witnessed the closest thing to a sample return mission from another star, without leaving home. Meanwhile, the sun would carry on exactly as before, its fusion engines completely unfazed. No temperature change, no dimming, no sign. It just consumed a piece of interstellar history. The star that powers all life on Earth would have swallowed something utterly foreign, digested it instantly, and continued shining as though nothing happened, its cosmic indifference at its finest. But for humanity, that indifference makes the event all the more meaningful. We'd have seen something that connects us, however briefly, to the rest of the galaxy. A fleeting moment when a traveler from another world met our star, burned bright, and told us a story before disappearing forever. For astronomers, it would be the kind of beauty that's both scientific and poetic. The realization that every flicker of light in the universe, no matter how brief, can teach us something about who we are, where we come from, and what's still out there, waiting to fall into the fire. For the sun, a collision with 3IATLAS would be like catching a mosquito in a bonfire. The sun weighs over 2 nonillion kilograms. That's a 2, followed by 30 zeros. An amount of mass so absurdly large that even trying to picture it feels like an exercise in futility. Meanwhile, 3IATLAS, though impressive by human standards, is a mere feather in the furnace. It might weigh a few billion tons, more than any mountain on Earth, but compared to the sun, it's less than a grain of dust on an elephant's back. The result? Nothing changes. The sun wouldn't wobble, dim, or even notice. If the sun were a celebrity, 3IATLAS would be that one fan who trips on the red carpet. Let's put the scale in perspective. The sun contains more than 99.8% of all the mass in our entire solar system. Every planet, asteroid, moon, and comet combined couldn't so much as make it blink. It's the gravitational anchor of everything that orbits it. To alter its balance in any meaningful way, you'd need to throw something at it that's, well, planetary. Even Mercury, the smallest planet, is 25 billion times heavier than 3IATLAS. So, if a tiny interstellar object were to hurl itself into the sun's plasma sea, the sun's response would be the astrophysical equivalent of, was that a bug? Stars like the sun are built to handle extremes. Every second, it consumes 4 million tons of its own hydrogen fuel, fusing it into helium and releasing energy equivalent to 96 trillion megatons of TNT. That's every single second. Against that backdrop, the addition of a few billion tons of rock and ice is microscopic, like tossing a teaspoon of sugar into the Pacific Ocean and expecting a measurable sweetness increase. From a physics standpoint, even the energy released by the impact of 3IATLAS, while enormous on human scales, barely registers in stellar terms. Let's say, hypothetically, the rock releases the equivalent of several billion nuclear bombs worth of energy as it vaporizes. That sounds catastrophic until you realize that the sun casually produces 1,000,000 times more energy than that in the time it takes you to blink. There's just no contest. The sun isn't just big. It's so far beyond our intuitive understanding of big that human comparisons collapse under their own weight. But there's another layer to the sun's indifference. Its nature as a self-regulating system. The sun isn't static. It's a constant balancing act between gravity, pulling inward, and the energy from nuclear fusion, pushing outward. This balance, called hydrostatic equilibrium, keeps it stable. Any tiny external disturbance, say the arrival of a space rock from another star, gets swallowed and dissipated instantly. The energy and matter from 3IATLAS would be absorbed into the sun's outer layers and redistributed evenly, like a raindrop merging with a lake. No shock waves, no stellar hiccups, just perfect, unbothered equilibrium. Even the sun's shape wouldn't change. You might imagine that an impact would cause a little bump or wave across its surface. But the sun isn't a solid ball. It's a massive sphere of gas and plasma. Waves of energy and magnetic turbulence ripple through it constantly, dwarfing anything that a tiny impact could generate. The sun's convection zone, where hot plasma rises and cooler plasma sinks, is a chaotic ocean of motion. In that constant churning, the remains of 3IATLAS would vanish instantly, its atoms mixed and melted into the soup. The only trace would be theoretical, a slight, momentary blip in localized density that even the most sensitive instruments would struggle to detect. To make the sun truly react, you'd have to hurl something absurdly massive at it. Imagine if Jupiter, the biggest planet in our solar system, were to somehow lose its orbit and spiral into the sun. Now, that would cause a reaction. one worth writing cosmic headlines about. The sun would absorb the planet, flare violently, and its luminosity might change for a time as new layers of material mix with its core. But 3IATLAS? It's more like a fruit fly compared to that hypothetical cosmic elephant. Still, there's something strangely elegant about this imbalance. It's a reminder of just how stable stars like the sun truly are. Our local star has endured solar flares, magnetic storms, comet impacts, and billions of years of relentless fusion without faltering. It's a cosmic engine that's been running smoothly since before Earth even existed. The arrival of 3IATLAS, while dramatic to us, would barely qualify as background noise to a being made of plasma and nuclear fire. And yet, within that indifference lies a fascinating paradox. Though the sun wouldn't react noticeably, it would still change in the tiniest, most imperceptible way. Every atom from 3IATLAS would become part of the sun's substance, however diluted. Over time, those alien atoms, born in a distant star system, shaped by cosmic radiation, traveling for millions of years, would merge with solar hydrogen and helium. They would take part in nuclear fusion, contributing their protons and neutrons to the sun's endless chain reactions. That means, in a microscopic sense, 3IATLAS would become part of the sun's light, a sliver of another world burning as part of ours. For astronomers, that's poetic. For the sun, it's Tuesday. If we had the ability to zoom in and watch the moment the last atoms of 3IATLAS disappear, we'd see nothing special, just plasma doing what plasma always does. The event would register as a flicker on a graph, a brief uptick in brightness that vanishes faster than it's noticed. And then, everything would return to normal. Solar flares arcing, sunspots bubbling, hydrogen fusing, light streaming outward across billions of kilometers. This calm indifference might sound anticlimactic, but it's exactly why stars like the sun are so extraordinary. They're built to be constant. Their power isn't in their reaction to events. It's in their ability to remain unaffected by them. 1 million cosmic accidents can occur in their vicinity, but they remain steadfast, turning chaos into radiance. The sun's serenity isn't weakness, it's dominance. It doesn't need to react because it's already in control of everything within its reach. So, while astronomers on Earth would celebrate the spectacle, and storytellers would romanticize the poetic end of an interstellar traveler, the sun would simply continue what it's been doing for 4.6 billion years, burning, shining, and keeping time for the universe. No applause, no fireworks, no self-awareness, just pure, steady fusion. If stars had personalities, the sun's would be the unflappable professional. Composed under pressure, impossible to impress, and always radiating confidence. You could throw a rock from another galaxy at it, and it wouldn't even look up from its nuclear paperwork. And that, perhaps, is the most humbling truth of all. The universe's greatest engines don't need to react to prove their power. They simply exist, and everything else bends, burns, or fades around them. While the sun shrugs off the impact, astronomers might detect tiny changes in solar emissions as the object vaporizes. Different elements, like carbon, oxygen, or iron, would briefly alter the sun's spectral fingerprint. It'd be like the sun singing one extra note in its nuclear song before returning to the same chorus. That fleeting chemical clue could tell us where the rock came from and what kind of star system it once called home. The universe, it turns out, has a habit of keeping records in light. Every atom, every reaction, every fleeting event in space writes its story, not in words, but in wavelengths. The sun's light, when broken down into its components, is like a barcode of cosmic identity. It tells us which elements are present, how hot they are, how fast they're moving, and even what magnetic fields are twisting them around. Astronomers have spent centuries learning to read this light, turning what seems like a blinding glare into a language of physics and chemistry. And for a brief, shining moment, the death of 3IATLAS would add a new verse to that song, a whisper from another solar system hidden in the sun's glow. Imagine the aftermath of the impact. 3IATLAS completely disintegrated. Its material dissolved into the solar plasma. Its atoms, alien in origin, mix with the hydrogen and helium that make up the vast majority of the sun. As those atoms become ionized, they start to emit light at very specific frequencies, depending on their type and energy state. Iron might produce sharp lines in the blue and ultraviolet, while carbon radiates in infrared and oxygen shines in ultraviolet. These lines are subtle, easily lost in the sun's blinding brilliance. But to the right instruments, they stand out like the brief flash of a firefly in a dark forest. Astronomers call these patterns spectral lines, and detecting them is like finding fingerprints in a cosmic crime scene. Normally, the sun's spectrum is remarkably consistent. Its light contains the same familiar lineup of hydrogen, helium, and trace elements. Its signature melody played on repeat for billions of years. But when something unusual enters that fiery mix, the song changes ever so slightly. New notes appear, discordant but beautiful, before fading away as the newcomer is absorbed. Capturing such a moment would require exquisite timing and precision. Observatories equipped with spectrographs, devices that split light into its component colors, would need to record the event in real time. Space telescopes like the Solar Dynamics Observatory or ESA's Solar Orbiter could detect these spectral shifts in ultraviolet, while ground-based instruments might pick up faint emission lines in visible or infrared wavelengths. For a few minutes, the sun's light would carry a foreign accent, a subtle hint that something not born in the system had joined the mix. What makes those fleeting chemical traces so valuable is what they can reveal. The exact ratios of elements, how much carbon compared to oxygen, how much nickel compared to magnesium, can tell scientists about the environment where 3IATLAS formed. Each solar system in the galaxy has its own unique recipe of elements, shaped by the type of star it orbits and the events that seeded its gas clouds. A system born near a supernova, for instance, would be rich in heavy metals like iron and silicon. A system formed in a quieter region might have more light elements like carbon and nitrogen. By analyzing the traces left behind, astronomers could effectively perform chemical archaeology on an object that no longer exists. It's astonishing to think that such delicate fingerprints could survive even for a moment in the sun's chaos. The solar atmosphere is a storm of plasma, where magnetic fields twist, particles collide, and temperatures soar into the millions. Yet in that chaos, order persists because physics always leaves a trail. Each atom that emits or absorbs light does so in a way that's utterly predictable. The universe may be violent, but it's not random. It's a perfectionist with a messy handwriting. For scientists, this data would be priceless. It would be the first time we could directly measure the elemental makeup of material from another star system after it's been vaporized in a star. Even though the object itself would be gone, its atoms would briefly tell their story through light before blending into the sun's greater whole. The event would give researchers a kind of before and after snapshot, what the sun's light normally looks like, and what it looks like when sprinkled with alien matter. That comparison could help refine models of stellar chemistry and even offer hints about how our own sun might someday interact with material from beyond. If the event were captured clearly, it could even help solve one of astronomy's subtler mysteries: whether interstellar objects like 3IATLAS tend to come from specific types of stars. Are most of them ejected from systems with giant planets like Jupiter? Or do they originate from younger, more chaotic systems where collisions are common? The chemical signature could hold the answer. A higher concentration of certain isotopes, for instance, might point to a red dwarf's planetary disk, while others could trace back to a supernova-enriched system. It's like tracing a traveler's accent back to their hometown, but on a galactic scale. Of course, the challenge isn't just detecting those traces, it's keeping them separate from the sun's own volatile rhythm. The sun is constantly changing, constantly flaring and pulsing with its own internal drama. Its surface boils with convection currents, and its magnetic fields generate loops and arcs of plasma that can alter its light in unpredictable ways. Distinguishing a few extra spectral lines from that background noise would be like trying to hear a single violin in a thunderstorm. But for the scientists dedicated to studying the sun, that's exactly the kind of challenge they live for. If successful, the result would be something profound. Direct evidence that the matter of one star system can merge, however briefly, with another. It's a glimpse into the cosmic recycling process that's been running since the universe began. Stars live, die, and scatter their material into space. That material forms new stars, new planets, and sometimes, just sometimes, goes on a billion-year journey across the galaxy before being reclaimed by another star. So while the sun might not notice, we would. In that tiny spectral shimmer, we'd see proof of connection, a physical reminder that the atoms forged in distant suns still wander and reunite. It's humbling and poetic all at once, a traveler's final whisper etched into the light of a star, echoing across space, saying, "I was here." If scientists could analyze those spectral signatures, we'd get a peek into another solar system's chemistry. Maybe 3IATLAS carries exotic isotopes, stuff we don't even find around here. It would be the universe's version of opening a message in a bottle, only the bottle is on fire, and the message is written in plasma. Still, that momentary flash could answer questions about how different stars build their planets. To most people, watching a rock burn up in the sun sounds like the end of the story. To astronomers, it's the beginning of a treasure hunt. The vaporized fragments of 3IATLAS wouldn't just disappear into the inferno. They'd release a brief but telling flare of energy that acts like a chemical confession. Each atom, when heated and stripped of its electrons, emits light at a specific wavelength. To the untrained eye, that light would look like a single blinding blaze. But through the instruments of science, it becomes a chorus of colors, each one revealing what the object was made of, and, indirectly, where it came from. This is how scientists decode the cosmic cookbook. Every star system has its own chemical flavor, influenced by the types of stars that enriched its neighborhood. When a star explodes in a supernova, it scatters heavy elements like iron, nickel, and gold into surrounding space. When smaller stars die more gently, they release lighter elements such as carbon and nitrogen. Over time, these materials mix, and new stars are born from the debris. The planets, asteroids, and comets that form around them inherit that chemical heritage. So, if we can study the composition of something like 3IATLAS, we're essentially tasting the recipe of its home star's environment. Let's say the flare from 3IATLAS revealed a high abundance of magnesium and silicon, elements that form rocky worlds. That might suggest it came from a system dense with terrestrial planets, places not unlike Earth or Mars. On the other hand, if its light showed excess carbon, oxygen, and methane, it might have been born in a region rich in ice and organic molecules, a frozen world at the edge of a red dwarf's dim glow. Each possibility paints a different picture of a faraway solar system, one we could never see directly. It's like identifying a family by the smoke from their kitchen. The real jackpot, though, would come from isotopes, those subtle variations of elements that act like atomic fingerprints. Hydrogen, for example, comes in two common forms: the lightweight version that fills stars and the heavier version, deuterium, that tends to form in colder, outer regions of space. The ratio of hydrogen to deuterium in 3IATLAS could reveal how close it once orbited to its star, or whether it spent eons in a frozen belt at the system's edge. Carbon and oxygen isotopes could tell us whether the star it formed around was hot and massive or small and cool. These are details even light years of distance can't hide. If 3IATLAS truly carried exotic isotopes, rare arrangements of elements not found in our solar system, it could hint at regions of the galaxy that evolved differently than ours. Maybe it formed in an environment blasted by frequent supernovae, where heavy metals are abundant. Or maybe it came from one of the Milky Way's older neighborhoods, where generations of star formation have long since slowed down, leaving behind only the sparse dust of ancient suns. Each scenario would expand our understanding of how varied or how similar the galaxy really is when it comes to building planetary systems. And beyond mere chemistry, there's a philosophical beauty in the thought. Somewhere, billions of years ago, dust and gas collapsed around a newborn star. In that maelstrom, tiny grains of minerals began to stick together. First pebbles, then boulders, then worlds. One of those fragments, perhaps from a collision or a gravitational skirmish, was ejected from its birthplace and sent drifting through the void. For eons it wandered, untouched, carrying within it the atomic memory of its home. Then, by sheer chance, it passed through our corner of the galaxy and met its fiery end in our sun. The information locked within its atoms was released, not into silence, but into light. That's the kind of cosmic poetry data can't help but write. From a purely scientific perspective, that light would be a revelation. Imagine being able to compare the elemental ratios from 3IATLAS with those found in Earth's meteorites or comets. We could see whether our solar system is average or an oddball in the galactic community. Perhaps our sun's chemistry is typical, a run-of-the-mill yellow star producing familiar ingredients. Or perhaps it's unique, with subtle differences that made Earth's life-bearing chemistry possible. Either way, 3IATLAS would offer a reality check, a chance to see how normal we really are in the grand galactic census. It could even reshape theories about how life's essential elements are distributed through space. If 3IATLAS carried complex carbon compounds, similar to the building blocks of life found in meteorites here on Earth, that would suggest such molecules are common ingredients across the cosmos. Life, then, might not be a rare fluke. It could be the natural consequence of chemistry repeating itself on every stage that has the right conditions. In a way, each interstellar rock becomes a small ambassador of possibility, carrying whispers of life's potential across the dark sea between the stars. But the reality of capturing that data is harsh. The sun's brightness, turbulence, and sheer heat make it nearly impossible to extract a clean signal. Detecting the fingerprints of 3IATLAS in the sun's glare would require instruments of incredible sensitivity and precision. Yet, even a partial detection, a slight spectral shift, an unexpected line of emission would be enough to spark years of research. Scientists would run simulations of its vaporization, reconstructing what the flash of light might mean. Did it contain rare isotopes? Was its dust unusually reflective? Could its elemental mix hint at a system more chemically evolved than ours? Each question would ripple through the astronomical community, feeding theories about how stars and planets form, evolve, and share their materials across the galaxy. Because that's the heart of it. The universe is constantly swapping its parts. Matter moves, collides, and blends across impossible distances. A rock born around a distant sun becomes vapor in hours. A cloud of atoms scattered by a dying star, billions of years ago, may one day become part of a new planet, or a curious creature wondering how it all began. 3IATLAS, in its fiery demise, wouldn't just tell us about another system's chemistry. It would remind us that, at a fundamental level, the universe recycles everything. Stars, planets, and living beings are all chapters in the same endless cycle of creation and renewal. So when that brief flare fades and the sun swallows the last trace of its visitor, what remains is not loss, but legacy. The data encoded in that flash, those interstellar clues, would stand as a testament to the connectedness of everything. From one star's death to another's birth, from dust to light, from unknown to known, the universe keeps writing its story. And sometimes we're lucky enough to read a line of it before the page turns to fire. Detecting 3IATLAS was hard enough the first time. It was faint, fast, and gone in a blink. If it were on a crash course with the sun, we'd probably only notice weeks in advance. Telescopes would scramble to track it. Solar observatories would prep their instruments. And the internet would go wild with interstellar object meets sun headlines. Humanity loves a good cosmic drama, especially one that doesn't threaten us personally. Spotting an interstellar object is one of the hardest games of hide-and-seek in existence. These visitors aren't glowing fireballs. They're dark, ancient lumps of rock and ice wandering through the void without any reflected light, until they're close enough for the sun to catch them in its beam. They don't politely announce their arrival either. One day, a telescope spots a faint, moving speck. The next day, it's already halfway through the solar system. Detecting one headed for the sun would take a perfect combination of timing, technology, and a little cosmic luck. That's because space, for all its emptiness, is visually noisy. Every night, telescopes scan the sky and detect thousands of moving objects, asteroids, comets, bits of space debris, and the occasional lost satellite. Most of these belong to our solar system and follow predictable paths. The tricky part is spotting the imposters, objects whose orbits don't fit. When astronomers realized 3IATLAS wasn't orbiting the sun, but instead slicing through the solar system on a one-time path, it immediately stood out. It wasn't from here. It was a tourist on a hyperbolic highway, just passing through. Now, imagine spotting that same kind of interstellar visitor, only this time it's not just passing. It's aiming directly for the sun. We probably wouldn't see it until it crossed into the inner solar system, somewhere near the orbit of Jupiter. That gives us, at best, a few months of warning. And even then, warning is the wrong word. There's nothing to warn about. It wouldn't be a threat to Earth. It would be a celestial spectacle, a natural experiment unfolding on a star-sized stage. When it first appeared, astronomers would likely argue about what they were looking at. Initial data would show a faint, fast-moving object, traveling on a path that curves sharply inward. Computer models would churn out predictions, some claiming it would swing past the sun and slingshot away, others suggesting a direct impact. As days passed and observations improved, the picture would sharpen. An interstellar object on a terminal dive into the solar furnace. That's when every observatory on the planet would turn its gaze toward the same spot in the sky. Telescopes designed for asteroid hunting, like the Pan-STARRS system in Hawaii or the Vera C. Rubin Observatory in Chile, would be the first to refine the object's trajectory. Space-based instruments like NASA's NEOWISE or the James Webb Space Telescope might attempt to study its infrared emissions, revealing its temperature and composition. Meanwhile, solar missions such as the Parker Solar Probe and the Solar Dynamics Observatory would start preparing for the main event, calculating when and where they'd have the best view of the impact. The excitement wouldn't stay in the science community for long. The moment the public heard interstellar object colliding with the sun, headlines would multiply faster than photons. News anchors would throw around words like unprecedented and historic. Documentarians would scramble to write scripts. Artists would render dazzling visualizations. And YouTube would become a galaxy of explainers, countdowns, and conspiracy theories. Some corner of the internet would, inevitably, insist it's an alien probe returning to its maker. Others would live stream the event with dramatic music and the words, "The sun will never be the same," even though, scientifically, it absolutely would. But beyond the hype, there would be a genuine sense of wonder. Humanity would be united, however briefly, by curiosity instead of fear. People would step outside to look at the same sun they see every day, knowing that somewhere up there, a tiny visitor from another star system was racing toward its fiery end. It's the kind of story that reminds us how vast and unpredictable the universe really is, and how small yet connected we are within it. In the days leading up to impact, the object would grow brighter as it approached. At first, it would appear as little more than a dim dot, even through powerful telescopes. Then, as sunlight began to heat its surface, gases and dust would sublimate, forming a glowing tail. 3IATLAS would briefly become a comet-like spectacle, a ghostly arc of light moving through space at extraordinary speed. Amateur astronomers would point their telescopes toward the skies, desperate to catch a glimpse. For once, the phrase, "It's getting hot in here," would apply on a galactic level. And then, just as suddenly, it would vanish into daylight. As the object drew too close to the sun, it would become invisible to optical instruments. Only space-based observatories shielded from the sun's glare would continue tracking it. Instruments capable of detecting ultraviolet and X-ray emissions would prepare to record the precise moment of impact. Scientists would coordinate across continents, syncing clocks to within milliseconds. They'd only get one shot at capturing data that could change our understanding of interstellar chemistry forever. The timing would be crucial. A few minutes too early, and they'd miss the flare. Too late, and the data would be drowned out by the sun's normal activity. The window for observation might last only seconds, but those seconds would contain more discovery potential than entire years of study. Every telescope, every sensor, every radio dish would be ready. It would be the solar system's biggest, brightest science experiment, unfolding 150 million kilometers away. And when the event finally happened, when the interstellar rock met the solar fire, the data would flood in like sunlight itself. Spectrographs would reveal the object's elemental composition. Energy readings would show how much heat and radiation it released. Every curve and spike in the graphs would be analyzed, debated, and compared. The images would go viral, turning the moment into a cultural touchstone. For a few days, science would trend worldwide, not because of fear, but because of fascination. Afterward, when the light faded and the headlines moved on, astronomers would still be poring over the data, teasing out every hidden secret in the patterns of light. The world might forget, but science never does. The story of 3IATLAS would live on, in research papers, in classrooms, in documentaries narrated by calm British voices. It would become a modern myth of curiosity, technology, and timing. The day humanity saw an interstellar messenger fall into the sun and caught the moment in data forever. And that's the quiet triumph in all this. We can't stop it. We can't touch it. But we can see it. We can understand it. In a universe where everything moves and nothing lasts, seeing it coming, even for a few short weeks, feels like victory. It's proof that out here on this small blue planet, we've learned not just to look up, but to listen for the whispers of travelers passing through the dark. Here's the good news. Even though the sun would get hit, there's zero chance of a chain reaction. The sun's fusion process is self-sustaining, but stable. Tossing in one rock, even a big one, won't trigger an explosion or change its life cycle. If anything, the sun would just use that extra material as fuel for a fraction of a second, then keep shining like nothing happened. Cosmic snack time, nothing more. It's easy to imagine the sun as a ticking bomb, waiting for some unlucky spark to set it off. After all, it's a giant sphere of hydrogen, burning at millions of degrees. Surely adding extra fuel would make it flare uncontrollably, right? Not quite. The sun isn't a bomb, it's a balance. Every second, it converts matter into energy through nuclear fusion. A process that sounds chaotic but is governed by an elegant equilibrium. Gravity pulls everything inward, trying to crush the sun under its own enormous weight, while the energy from fusion pushes outward, holding it up. That tension is what keeps the sun stable. When something like 3IATLAS crashes into it, that equilibrium doesn't even flinch. The sun's core, where fusion actually happens, is buried deep beneath hundreds of thousands of kilometers of plasma. The outer layers, the photosphere, chromosphere, and corona, are just the visible frosting on a cake, whose real power lies far beneath. For an impact to affect the sun's fusion rate, the incoming object would have to somehow deliver its energy directly to the core. That's like tossing a pebble into a volcano and expecting to reach the magma chamber. The sun's density is so immense that anything falling in is vaporized, ionized, and mixed into the outer plasma long before it comes close to the heart of the star. To understand why the sun doesn't overreact, you have to look at how fusion really works. The sun's core is unimaginably dense, around 150 times denser than the water, and about 15 million degrees hot. Under those conditions, hydrogen atoms move so fast and collide so violently that they fuse into helium, releasing energy in the process. But the fusion rate depends entirely on pressure and temperature. A small addition of material doesn't suddenly crank up the thermostat. It's like throwing a snowflake into an oven that's been running steadily for billions of years. It won't notice. And the sun's internal thermostat is self-regulating. If something caused the fusion rate to increase, the extra energy would make the core expand slightly, lowering its density and temperature. That slows fusion back down. If fusion slowed too much, gravity would pull the core inward again, raising its temperature and restarting the process. It's an incredibly stable feedback loop, a cosmic version of cruise control. So no matter what you toss in, the sun adjusts almost instantly, smoothing out any disruption. It's the ultimate example of a system that's too big to overreact. That's not to say the idea of chain reactions in stars is completely imaginary. It's just that our sun isn't that kind of star. Truly unstable stars exist. Some massive ones, dozens of times heavier than our sun, do experience runaway reactions. They fuse heavier elements in layers until their cores can't sustain the pressure. Then gravity wins, the star collapses, and the result is a supernova, a cataclysm that makes our sun look like a nightlight. But the sun is a middleweight, built for longevity, not drama. It fuses only hydrogen and helium, avoiding the nuclear domino effects that doom its larger cousins. It's like the responsible older sibling in a family of pyromaniacs. Even if 3IATLAS was somehow gigantic, say the size of Mount Everest or larger, the energy it carried would still be negligible compared to what the sun burns every second. At most, the impact would create a localized disturbance, a brief bright spot, a puff of plasma, maybe a ripple in the magnetic field. But the overall fusion rate? Unchanged. To put it in perspective, the sun converts 4 million tons of matter into pure energy every second. That's enough power to run human civilization for millions of years. A few billion tons of interstellar rock barely registers in that context. It's the equivalent of adding a single drop of water to a boiling ocean and expecting a tsunami. If anything, the sun would handle the event with its usual calm efficiency. The incoming material from 3IATLAS would be absorbed and redistributed, its atoms merging seamlessly with the solar plasma. A handful might sink slightly deeper, but they'd soon become part of the endless convection currents that churn the sun's outer layers. Within minutes, the newcomer's identity would be erased. The only evidence it was ever there would be the faint flare of light seen by distant telescopes. A brief exhale before business resumed as usual. It's a comforting thought, really. The sun doesn't panic. It doesn't explode or implode when something hits it. It simply continues doing what it's done for the past 4.5 billion years, turning hydrogen into light, calmly and reliably. Our lives, our seasons, our entire ecosystem depend on that stability. And it's reassuring to know that even an interstellar visitor barreling into it headfirst can't shake that rhythm. The sun's temperament is stellar zen, unbothered by everything, from comets to cosmic debris. The idea of a chain reaction might make for good science fiction, though. Imagine a film where an interstellar rock plunges into a star and sets off a cascade of runaway fusion, igniting a superflare that changes the course of history. It's dramatic, apocalyptic, and wildly inaccurate, but irresistible to the imagination. The truth, as usual, is less explosive, but far more impressive. The sun's steadiness isn't boring, it's miraculous. It shows us that nature can create something both unimaginably powerful and perfectly balanced. Of course, that stability won't last forever. In about 5 billion years, the sun will naturally exhaust its hydrogen fuel. When that happens, no interstellar object will be to blame. It's just the slow clockwork of stellar evolution. The sun will swell into a red giant, engulf Mercury and Venus, and scorch whatever's left of Earth. Then it will shed its outer layers and collapse into a white dwarf, glowing faintly for trillions of years. But until then, it will continue burning steadily, immune to the chaos of passing visitors. So if 3IATLAS were to crash into it tomorrow, there'd be no apocalypse, no ignition of solar doom. The sun wouldn't flare out of control or change color. It wouldn't even hiccup. It would simply absorb the rock, shine a little brighter for a heartbeat, and carry on. The universe doesn't do dramatics where they're not deserved. Some things are built to last, and our sun is one of them. The chain reaction that never happens is, in truth, the reason we're here to imagine it in the first place. Now, here's a fun what if. If the impact happened in a magnetically active region, it might disturb the sun's surface enough to spark a flare, a burst of energy that could ripple through space. Imagine a spark lighting a campfire that was already smoldering. The sun's magnetic fields twist and snap constantly. A well-timed visitor could, in theory, add some chaos to the mix. But that flare would be entirely natural. The cosmic equivalent of saying, I was gonna erupt anyway. The sun isn't just a giant ball of fire. It's a magnetic monster. Its plasma churns and writhes, dragging magnetic field lines into wild shapes. These tangled magnetic fields occasionally snap and reconnect, releasing immense amounts of energy in the form of solar flares. When that happens, it's like the sun sneezes photons across the solar system. Those bursts can disrupt satellites, ignite auroras, and temporarily overload power grids here on Earth. But they're not random. They're the result of immense magnetic tension built up over days or weeks, stored energy just waiting for a reason to release. Now, imagine 3IATLAS plunging toward the sun, not into a quiet region, but right into one of those zones of magnetic tension, a sunspot region bubbling with energy. Could its arrival push the sun over the edge? Possibly, though the distinction matters. The flare would still be the sun's own doing. The interstellar rock wouldn't create the energy. It would merely act as a trigger. Think of it like tapping an already overfilled balloon. It doesn't make the explosion. It just provides the excuse. To understand why that's even a possibility, you have to picture what a solar flare really is. Beneath the sun's surface, plasma, electrified gas, circulates in enormous currents. That motion generates magnetic fields that twist together like braids of invisible rope. Over time, those fields become tangled, storing energy like a stretched rubber band. When the tension gets too high, the field lines snap and reconfigure, releasing energy equivalent to millions of nuclear bombs in seconds. The result is a solar flare, a flash of X-rays, ultraviolet radiation, and charged particles shooting off into space. If 3IATLAS were to hit such a region, its entry could cause localized turbulence, shock waves rippling through plasma already on the verge of erupting. The heat, motion, and disruption from the impact might destabilize a magnetic field line that was already straining. The sun doesn't need much of a nudge to release its pent-up energy. The pressure is always there, waiting for something to break the tension. A small impact at just the right place and time could, theoretically, be that nudge. Of course, the flare itself wouldn't owe its power to 3IATLAS. The sun is the one doing the heavy lifting. Its magnetic fields are unimaginably strong. A moderate solar flare releases around 10 to the 25th joules of energy, roughly the equivalent of 100 million hydrogen bombs. Compared to that, the kinetic energy of 3IATLAS is microscopic. It's like a fruit fly colliding with a lightning bolt and taking credit for the thunder. The flare would have happened eventually. The rock would just be an incidental guest star in the sun's ongoing performance. Still, it's a thrilling thought experiment. Picture the moment of collision. 3IATLAS, slamming into a magnetically active patch of the sun, sending waves of disturbance through its surface. In that instant, magnetic field lines snap upward, releasing a jet of plasma thousands of kilometers high. Telescopes across the solar system record the event in every wavelength: radio, X-ray, ultraviolet. Earth's magnetic field feels the echo hours later as the flare's electromagnetic pulse washes across space. Satellites briefly flicker, auroras ripple near the poles, and somewhere, a scientist watching the data feed realizes they've just witnessed a cosmic coincidence of spectacular timing. An interstellar rock arriving precisely as the sun decided to flex. If this scenario played out, the effect on Earth would depend on the direction of the flare. Solar flares are like spotlights. They erupt in specific directions, not uniformly. If the flare happened on the side of the sun facing Earth, we'd get an intense burst of radiation, but nothing catastrophic. Earth's magnetic field and atmosphere are excellent shields. At most, high-frequency radio signals might flicker, satellites might go into safe mode, and the night skies would dance with auroras that stretch far beyond the poles. If the flare happened on the far side, we'd only see its reflection, a ghostly glow recorded by orbiting observatories. The fascinating part isn't just the physics, it's the choreography. The sun's surface is never still. It rotates once every 25 days at the equator and slightly slower near the poles, twisting its magnetic fields like taffy. Every 11 years, those magnetic patterns flip, leading to cycles of solar calm and solar chaos. Right now, as humanity watches from its fragile blue perch, we're in one of the active phases, a time when sunspots, flares, and coronal mass ejections are common. If 3IATLAS were to arrive during one of these fiery peaks, its odds of colliding with an already primed region would be higher. The sun, in that case, might not just absorb it. It might use the opportunity to put on a light show. But, again, it's crucial to remember the scale. The sun doesn't need external help to erupt. It's already doing it all the time, tossing out flares as casually as sighs. The arrival of 3IATLAS would be, at best, a whisper that coincides with a roar. The flare would happen on the sun's schedule, powered by its own magnetic complexity, not by the small visitor falling into its fire. Yet, the symbolism is irresistible. A traveler from another star plunges into ours, and the result is a burst of light that races outward, visible across millions of kilometers, a handshake between stellar systems, written in plasma and energy. The flare would fade within minutes, its light dissipating across the solar system, but its data would linger, studied for years. Scientists would debate whether the impact had any measurable effect. And while most would conclude, probably not, they'd still smile at the poetic possibility that, for a brief instant, two cosmic forces, one colossal, one small, had danced together. In the end, if 3IATLAS triggered a solar flare, it wouldn't be a disaster or a miracle. It would be physics in motion, the sun doing what it does best, transforming tension into brilliance. The interstellar visitor wouldn't cause chaos. It would simply arrive at the right place, at the right time, in the right kind of storm. And maybe, just maybe, that coincidence would remind us that even in a universe ruled by laws, there's still room for timing that feels almost poetic. A spark striking a flame that was always meant to burn. Interstellar objects probably pass through our solar system more often than we think. Most just drift by unnoticed, tiny and dark. The sun likely swallows a few every millennium, quietly absorbing the leftovers of other star systems. It's like the universe's recycling program. Old worlds broken apart, their fragments feeding new ones. Every piece that falls into the sun becomes part of its glow, fueling future photons that will someday touch Earth's skies. It's easy to forget that our solar system isn't isolated. It's more like a busy intersection in a galactic city. The Milky Way is full of wanderers, icy fragments ejected from forming planets, rogue comets flung from unstable orbits, and ancient asteroids cast adrift after their stars died. Over billions of years, these travelers crisscross the galaxy, passing through regions like ours before disappearing again into the dark. Most are invisible, too small and too dim to catch even the keenest telescope. But statistically, they must be out there, thousands, perhaps millions, gliding silently between the stars, occasionally pulled off course by the gravity of a sun like ours. When one of these wanderers ventures too close to the sun, there's no grand explosion or warning. Gravity takes over. The object accelerates, heating up as solar radiation bombards its surface, until it either slingshots away or plunges straight in. Those that make it all the way are devoured instantly, vaporized long before they ever reach the visible surface. Their atoms scatter through the corona, merging seamlessly into the solar plasma. It's not a violent end, at least from the sun's perspective. It's dinner. Astronomers call such objects sun grazers or sundivers, and while most originate from our own solar system, it's inevitable that a few have come from farther afield. Comets from the Oort cloud, for instance, are already on the edge of interstellar space. When gravity from passing stars or galactic tides nudges them inward, they plunge toward the sun, following long, looping paths that can take millions of years to complete. But, occasionally, one of those paths doesn't loop. It comes straight in from outside the solar system entirely. And when that happens, the sun doesn't discriminate. Native or foreign, all are welcome in its blazing embrace. If we could somehow see all the objects the sun has consumed over its lifetime, it would be staggering. Not just a few comets or asteroids, but the remnants of entire ancient systems. Every particle of dust, every icy grain, from a distant star's nursery that wandered too close, has joined the sun's mass. Over billions of years, these small meals have subtly altered the sun's composition. Not enough to change its nature, but enough to leave a record written deep in its structure. You might even say the sun carries a faint cosmic accent, shaped by everything it has devoured since its birth. This quiet consumption isn't unique to our star, of course. Across the galaxy, every sun feeds in the same way. Some stars, surrounded by dense debris fields, gorge themselves regularly, swallowing planets and asteroids whole. Others, drifting through empty space, may go eons without a single meal. When astronomers look at stars and find unusually high levels of heavy elements, metals like iron, magnesium, or silicon, it's often a sign that they've recently devoured something rocky. Those chemical signatures are the fingerprints of fallen worlds, preserved in the light of the stars that consumed them. The sun, by contrast, is a moderate eater. It doesn't crave destruction. It simply waits. Its gravity is patient, its appetite infinite but unhurried. Most of what it swallows comes not from cataclysm, but from cosmic inevitability. Tiny nudges that send debris tumbling inward over millions of years. Occasionally, a larger feast arrives, like a comet tens of kilometers wide. These make for short-lived spectacles, bright streaks of light across solar observatory cameras, brief flares of ultraviolet radiation. But even these grand finales are drops in a stellar ocean. For the sun, a million-ton comet is a single crumb, and yet there's something almost spiritual about that. Every atom that falls into the sun is reborn as light. It doesn't matter if it came from a comet born in our solar system or a rock that wandered here from another galaxy. It all becomes part of the same radiance. The sunlight that warms your face might contain energy once locked inside alien minerals, forged around a star that died before Earth existed. It's an idea so grand and humbling, it borders on poetic. We live under a sky illuminated by the recycled remnants of other worlds. The sun's appetite for wanderers also plays a hidden role in the evolution of the solar system. When interstellar debris passes through, it doesn't just fall inward. It interacts with the planets along the way. Some fragments might be captured temporarily by Jupiter's immense gravity, becoming temporary moons or splitting into smaller pieces. Others might collide with asteroids or comets already orbiting the sun, reshaping them in subtle ways. In this sense, the sun isn't merely a destroyer. It's the gravitational conductor of a cosmic symphony, orchestrating encounters that mix and redistribute material throughout the system. And then there's the sheer timescale of it all. The sun has been shining for roughly 4.6 billion years and will continue for about 5 billion more. In that time, it will likely consume countless more wanderers. each one carrying its own ancient history, each one adding infinitesimally to the sun's mass. To the sun, these encounters are routine. To us, they're reminders that nothing in the universe truly stands still. Every atom moves, drifts, and transforms, cycling through stars and space endlessly. We often think of the sun as static, a constant presence in our sky. But it's not. It's a living furnace, always changing, always consuming. The photons it emits today were born deep in its core tens of thousands of years ago, taking millennia to fight their way to the surface before racing through space at the speed of light. Somewhere in that endless stream of energy might be the faintest trace of an interstellar traveler, its atoms fused, its story now woven into the light that paints our mornings and powers our lives. So yes, the sun is hungry, but not in the destructive way we imagine. Its appetite is patient, its diet cosmically balanced. It devours the past and turns it into the present, melting the fragments of forgotten worlds into the glow that sustains ours. Every sunrise, in a sense, is proof of that quiet cosmic feast, the light of 1,000 fallen wanderers shining down on the one planet lucky enough to notice. From Earth, it would be a once-in-a-lifetime light show. Space telescopes would capture the moment in ultraviolet, while solar probes like Parker might even feel the blast wave. For a few hours, the world's science community would be glued to monitors, watching the universe's equivalent of a car crash in slow motion. The memes alone would be glorious. Sun eats interstellar rock, rates it 1 out of 10 for flavor. But make no mistake, this wouldn't be just another pretty cosmic event. It would be one of the rare moments when humanity could watch the laws of the universe unfold in real time. Imagine the excitement, an interstellar object, born around another star, completing its billion-year journey by diving into our own. Every observatory, from the deserts of Chile to the frozen peaks of Mauna Kea, would turn toward the sun, tracking the faint glimmer of 3IATLAS as it made its terminal approach. In the weeks before impact, astronomers would chart its path with precision, bordering on obsession. Every pixel from every telescope image would be analyzed, its orbit recalculated, its speed refined. It would become the most studied rock in the cosmos, its impending destruction only adding to the anticipation. As it neared the sun, the object would brighten, shedding material and developing a faint tail, glowing with reflected sunlight and vaporized gases. For those watching the data unfold, it would be like tracking a candle racing toward a furnace. As the big moment approached, the world would divide neatly into two groups: the scientists and everyone else. The scientists would be calmly, well, mostly calmly, discussing radiation wavelengths, temperature curves, and spectroscopic calibration. The rest of the planet would be posting countdowns, making reaction videos, and speculating wildly about what might happen when the rock hit the sun. Could it cause a solar explosion? Someone would ask on social media. Could the sun burp out a chunk of it and hit Earth? Another would add. Scientists would patiently explain, again, that no, the sun isn't going to explode, and no, we're not about to be flash fried. But secretly, even the experts would feel that giddy, rare thrill of witnessing something that's both harmless and awe-inspiring on a cosmic scale. The moment of impact would be invisible to the naked eye. No one could look directly at the sun without blinding themselves, but instruments built to study our star would catch every nuance. NASA's Solar Dynamics Observatory would record the ultraviolet flash. The European Space Agency's Solar Orbiter might capture the plume of vaporized material rising and folding into the solar plasma. The Parker Solar Probe, swooping through the sun's outer atmosphere on its daring orbits, could literally feel the shockwave, a brief tremor in the sea of charged particles that surround the star. It would be the closest thing to touching an interstellar object as it died. And here's the beauty of it. Even though the impact would last mere seconds, the world's observatories would stretch that moment out indefinitely. Instruments would collect terabytes of data, freezing time so scientists could examine each stage of the event in microscopic detail. The object's glow would reveal its composition, its breakup sequence, and its final transformation into plasma. Each dataset would become a window into a story billions of years old, a story written by physics, erased by fire, and preserved in light. Meanwhile, the public's fascination would hit a fever pitch. The internet would erupt in real time, live streams, animations, endless posts comparing the event to the sun's latest snack. Late-night hosts would crack jokes about cosmic dining habits, while science communicators would rush to explain the sheer improbability of what we were witnessing. For once, the world's collective attention would be fixed not on crisis or catastrophe, but on wonder, a peaceful spectacle that united curiosity instead of fear. News agencies would broadcast real-time updates, graphs of the sun's energy output, visualizations of the flare, and commentary from scientists who, for a change, wouldn't have to say, "We're not sure yet," about what might happen. They'd know exactly what was happening and why, and that would make it even more mesmerizing. Even without visible fireworks, the sense of scale would be overwhelming. A tiny fragment from another star system, falling into one of the most powerful forces in existence. A few hours after the event, the data would begin to pour in. Spectral analysis would reveal exotic ratios of elements, maybe even confirming that the object carried isotopes unfamiliar to our solar system. The solar flare caused by the collision, if there was one, would ripple outward, brushing against Earth's magnetosphere days later, sparking auroras and a new round of headlines. Interstellar impact lights up polar skies. Scientists would gather in video calls and conferences, giddy with discovery, swapping early findings and speculating on the origin of their new favorite visitor. And of course, art and culture would follow. You can practically see the flood of digital tributes, paintings, music, documentaries, short films, and sci-fi stories inspired by the event. Poets would write about a rock's final journey into the sun. Filmmakers would dramatize the long voyage from one star system to another. For a few months, humanity would collectively remember that we live in a galaxy full of motion, connection, and story. Then, slowly, the excitement would fade. The world would move on to new stories, new discoveries, new distractions. But in laboratories and universities, the legacy of that day would live on. Researchers would analyze the data for decades, refining models of how interstellar material behaves, how solar plasma reacts, how the sun digests foreign matter. The collision would become a reference point, a cosmic case study for generations of scientists to come. And maybe, years later, someone would look up at the sun, knowing that buried somewhere in its light are atoms from a world that once orbited another star. They'd realize that what they were seeing wasn't just sunlight. It was history, recycled and reborn, shining across the void to reach us. If we ever got to watch that happen, to truly witness it, it would remind us why we study the cosmos in the first place. Not just to measure it, not just to understand it, but to feel it. To look at something unimaginably vast and remember that we're part of it too. A small planet orbiting a patient star, watching the universe do what it does best. Turn endings into beginnings, and fire into light. In the end, 3IATLAS's fiery death would be both an ending and a beginning. A rock that traveled across galaxies would vanish into starlight, its atoms scattered among the sun's plasma, destined to one day help light another dawn. It's a reminder that even in destruction, the universe recycles everything. Stars eat, burn, and shine, and we, orbiting in their glow, get to watch the grand show. The cosmos, it seems, never lets anything truly disappear. It just rewrites the script in fire. Picture it. A mountain-sized fragment of another world, drifting through darkness for perhaps 1 billion years, finally finds its destination, not on a planet, not in a collision with another asteroid, but in the very heart of a star. Its journey ends in light. What was once cold, solid matter, dust, minerals, frozen gases, becomes radiant energy scattered across the solar system as part of the sun's eternal blaze. Those atoms that once wandered through the interstellar night now join the chorus of photons streaming outward, touching planets, moons, and spacecraft, including ours. In the most literal sense, the interstellar traveler becomes part of our daylight. There's something profoundly poetic about that transformation. For so long, 3IATLAS had no purpose, no destination. It was a cosmic vagabond, drifting aimlessly through the galaxy. Yet, its end gave it meaning. It became part of something larger than itself. In a universe that tends to forget its smaller players, it's almost comforting to think that even a lonely rock can earn a final act that leaves a mark, however small, on a star's story. If we could zoom in on the moment after impact, we'd see its remnants swirling, dispersing into the sun's plasma currents. Each atom stripped of its electrons, each nucleus tossed into the roaring convection zones that churn the sun's outer layers. Those atoms won't remain still. The sun is in constant motion, its interior behaving less like a solid and more like a boiling ocean. Convection currents rise and fall, carrying heat, light, and matter toward the surface. In time, some of 3IATLAS's components, its carbon, oxygen, and silicates, would diffuse evenly throughout the sun, becoming indistinguishable from the material that's been there since the beginning. That diffusion process isn't just blending, it's rebirth. The elements of 3IATLAS would join the nuclear ballet of fusion, contributing in some infinitesimal way to the creation of photons. Those photons would begin their long, slow journey outward, bouncing between particles for tens of thousands of years before escaping into space. And when they finally reach the edge of the sun, they'd radiate outward in all directions, some toward empty space, some toward Jupiter, some toward Earth. Maybe, just maybe, a few of them would hit a leaf, a solar panel, or a human face. The light of a fallen interstellar wanderer would warm our planet, mingle with our mornings, and illuminate our lives. It's humbling to realize that this process, the death of one object fueling the life of another, is the backbone of the universe. Stars consume matter, emit light, and eventually die, scattering their material to form new stars and planets. Everything cycles. Our sun, too, was born from the ashes of stars that came before it, their remains condensed into the gas cloud that became our solar system. So, in a way, 3IATLAS, returning to a star, is just the continuation of that same ancient rhythm. Its atoms came from stars long dead and are now returning home to join another that still burns. This endless recycling is what makes the cosmos feel alive. There's no true loss in space, only transformation. A star's light becomes energy for worlds. A planet's debris becomes the seed of another system. Even black holes, the supposed endpoints of everything, may someday leak their contents back into the universe through evaporation. In that vast, ongoing story, 3IATLAS is just one line of dialogue, brief, brilliant, and complete. For humanity, watching such an event would be both scientific and spiritual. We'd marvel at the physics, the spectroscopy, the data, the fusion dynamics, but we'd also feel something deeper, a sense of kinship with the fallen traveler, because in a strange way, we're made of the same material. The calcium in our bones, the iron in our blood, the oxygen we breathe, all forged in ancient stars. We too are fragments of other worlds, reassembled into consciousness. When we watch a rock from another system burn in the sun, we're witnessing a reflection of our own origins, a reminder that we belong to this great cosmic cycle of birth and destruction. Somewhere in another galaxy, there might be another sun, another civilization looking up at their own sky, watching a similar interstellar visitor meet its end. Maybe they feel the same wonder we would, the same recognition that all things eventually return to light. It's one of the rare universal truths that doesn't depend on language or species. Everything that lives, shines, or drifts is part of the same grand exchange. And though the event would pass quickly, its symbolism would linger. Scientists would continue to analyze its data. Artists would draw inspiration from it. And storytellers would spin new myths about travelers and fire. For generations, it would stand as a moment where science and poetry met. The proof that the universe isn't cold and indifferent, but beautifully consistent in its creativity. When the last traces of 3IATLAS dissolve completely, the sun will keep shining, unchanged yet slightly richer. Another meal digested, another story absorbed. Its light will continue to flow outward, carrying with it the smallest whisper of that ancient traveler's journey. We'll never see those atoms again, but we'll feel them. Each dawn, each glint on the ocean, each shimmer on a city's glass towers. So perhaps goodbye isn't quite right. In the cosmos, there are no real farewells, only transformations. 3IATLAS didn't vanish. It became part of the light that will continue for billions of years. That's the universe's quiet genius. It turns endings into beginnings and makes immortality out of motion. The traveler's story ends in flame, but the light it helped to create will keep moving, forever outward, forever telling us that even in the grandest fires, nothing is truly lost.